For this question, we want to use logarithmic differentiation to differentiate the function with respect to x. As we look at this problem, if we use our original derivative rules, you would have to use the product rule because of these two expressions, and within each factor, you would have to use the chain rule, which makes this a slightly complicated derivative to calculate because of you combining those rules. So with this question, the directions are asking you to use logarithmic differentiation. And with logarithmic differentiation, we're able to use a little bit of algebra before calculating the derivative, which simplifies the expression significantly. And then when you calculate the derivative, you don't have to use as many rules combined. So with logarithmic differentiation, your first step is to take the derivative on both sides. I'm sorry, let me back up. Take the log of both sides, and I'm going to use natural log because the rule for natural log, the derivative rule for natural log is a little simpler than other logs. So I'm taking the log on both sides. And what this allows me to do is it allows me to introduce the log, and the log has properties for simplifying expressions with product, quotients, and powers. So the rules that we're going to use are those product, quotient, and power rules for logarithms. So I'll start with the product rule because we have a product. This is the product of x to the 5th plus 5 squared and the square root of 2x plus 3. And this product rule for logarithms allows me to write this as two separate logs. So log of the first factor, natural log of the first factor, plus natural log of the second factor. And I'm going to go ahead and change that radical, that square root, to the 1/2 power. So I just used the product rule for logarithms to break that into two separate logs. And now I'm going to use the power rule for logarithms because we have a power inside the logarithm. And the power rule allows me to bring that power down to become the coefficient. So this is the power rule for logarithms. This is an algebra rule, not a derivative rule. And I did the same thing for the second one. We had a power of 1/2, and I made that the coefficient. Okay, so now that we have used the power rule and the product rule, we're going to calculate our derivative. Now, we're going to calculate the derivative with implicit differentiation. Originally, the equation was written in explicit form. Explicit form is when you have y equals and the only variable within your equation is x, so we have explicit form. However, when we took the log of both sides, that is no longer in explicit form. We no longer have just y equals, we have natural log of y equals. So because the equation is now written in implicit form, we have to follow implicit differentiation to calculate the derivative. I'm going to calculate the derivative on the left with respect to x, and I'll calculate the derivative on the right with respect to x. On the left, we're taking the derivative of natural log, and the derivative rule for natural log is the derivative of the inside over the inside. So the derivative of this will be y prime over y. The derivative of y over y. We'll do the same thing on the right. We do have logs on the right. We'll carry down that constant multiple of 2, follow the derivative rule for natural log. The derivative of the inside would be 5x to the 4th over the inside x to the 5th plus 5. Carry down that constant multiple of 1/2 and follow the derivative rule for natural log. That's the derivative of the inside, which is 4x, over the inside, 2x squared plus 3. We can do a little simplifying here to make this y prime over y equals 10x to the 4th over x to the 5th plus 5. And then here 2 cancels with 4, making this 2x over 2x squared plus 3. Our goal was to calculate the derivative of y, so I'm going to multiply both sides by y. And that gives me y prime is equal to y. I can go ahead and substitute the value of y. That was the original equation. The original equation was y equals x to the 5th plus 5 squared times the square root of 2x squared plus 3. And I'm copying this down. So we have now calculated the derivative. The derivative of y is x to the 5th plus 5 squared times the square root of 2x squared plus 3 times the quantity x squared, 10x to the 4th over x squared plus 5 plus 2x over 2x squared plus 3. So this is the derivative. I'm going to continue to simplify this derivative, and the reason why I want to continue to simplify is because I have a denominator here with a factor of x squared plus 5, and we have a factor of, I think I have copied that wrong. Let me correct that. That should be x to the 5th plus 5. So we have a factor of x to the 5th plus 5 and a factor of x to the 5th plus 5 here. So if I'm able to do a little algebra simplification, I may be able to combine some of these factors together. You can see a similar thing here. We have a factor of 2x squared plus 3, and inside the radical we have a factor of 2x squared plus 3. So the simplifying that I'm going to do involves getting a common denominator for the terms on the right. I'm also going to keep this in having an exponent instead of a radical, so that when I get to the point where I combine things together, I'll be able to do it easily. On this right-hand side here, this right factor, I'm going to get a common denominator between these fractions. And what I'll do is I'll multiply this denominator times this numerator. And I'll multiply this denominator times this numerator to combine those fractions together. That's finding a common denominator. So that's 10x to the 4th times 2x squared plus 3 plus 2x times x to the 5th plus 5. And that's all over our common denominator of x to the 5th plus 5 times 2x squared plus 3. So now that I've gotten that common denominator, I'm going to be able to cancel one factor of x to the 5th plus 5 with this factor here. So now I only have one factor of x to the 5th plus 5. I'm also going to be able to combine this factor in the numerator with this factor in the denominator. Since they have the same base, I'll subtract the exponents. So I'm doing 1/2 minus 1. That's 1/2 minus 2 over 2, and that's a negative 1/2. I'll have a factor of 2x squared plus 3 to the negative 1/2 power. And then in the numerator, I'll do a little distributing and combining like terms. That would be 20x to the 6th plus 30x to the 4th plus 2x to the 6th plus 10x. I'm copying this down and I have some like terms I can combine. Got 20x to the 6th combining with 2x to the 6th to get 22x to the 6th plus 30x to the 4th plus 10x. Within that factor, we do have a common factor. These are all even, so I can factor out a 2. And they all have an x, so I can factor out an x. So I'm factoring out a 2x. That leaves me with 11x to the 5th plus 15x cubed plus 5. I'm going to write the final derivative here, and that's going to be 2x times x to the 5th plus 5 times 11x to the 5th plus 15x cubed plus 5. And in the denominator, I'm putting this factor in the denominator because of the negative in the exponent. I would have square root of 2x squared plus 3. So that is the final simplification for my derivative. Thank you for checking out my videos. Have a great day.